So today we have Rahul Jan with us, and he will present his work on first principle investigation of interfacial chemistries in metal sulfur batteries. So before starting, I will introduce him with you briefly. So Rahul Jan is a third-year PhD student in the Department of Mechanical Engineering at Wayne State University. So his PhD works focuses on computational electrochemistry, mostly on lithium and sodium-sulfur battery, electrode and electrolytes. In his PhD so far, he has published 17 journal articles. Along with this, he has received several scholarships and awards. Particularly in this year, he has received prestigious Ralph Kammler Award for being the best graduate student. He was also nominated Thomas C. Rumble University Fellowship twice. Before starting his PhD, he did his bachelor's in chemistry and electrochemical engineering from Central Electrochemical Research Institute, India. So there he worked on investigation of electrochemically active electrode materials for lithium and sodium-ion batteries. So I think today's talk will be a great introduction to the students who are enthusiastic in energy storage chemistry, which is currently a booming field because of renewable energies and EVs. So I will welcome Rahul, and you can start your presentation now.
Hello, Shadir. Can you hear me?
Yeah, I can hear you. Yeah.
Okay. Thank you. So, good morning to all present here. So, thank you for giving me this wonderful opportunity to present in this prestigious MMMRN webinar series. So, I'm Rahul Jain, working under the guidance of Dr. Mahbub Islam in a Prism lab at Wayne State University. So my topic for today's discussion is electrocatalysis in metal sulfur batteries, talking on the perspective of DFT. So let's go directly to the top. Okay, so before going to the energy storage and energy conversion, let's talk a little bit about the electrochemistry. Electrochemistry is a branch of physical chemistry which deals with the study of the chemical reaction which is happening at the interface of the electrode and the electrolyte. An electrode can be a metal, a semiconductor, or anything, and the electrolyte, particularly, we use it as an ionic conductor, a medium to conduct the ions. And it's basically the relationship between the chemical energy as well as the electrical energy, the interconversion between them. So far, the electrochemistry, we are using a wide range of applications like sensing, corrosion, organic electrosynthesis, industrial electrocatalysis, energy conversion, energy storage. Particularly in our lab, we are working on energy storage and energy conversion. As you can see there, they are actually interrelated, correlated to each other. Because once we produce energy, we need to find a way to store them, and vice versa. So electrochemistry back in 2019, we have received a very high recognition after the receiving of the Nobel Prize for this three renowned professors. So now let's go to the energy storage system. So in the initial days, researchers thought that, okay, the initial challenge is to find whether the sustainable chemistry is competitive or not. So this is a report from Fraunhofer Institute where you can see that the energy which is coming from the wind as well as the solar is more competitive and comparable to coal. Then people thought that, okay, the sustainable chemistry is competitive or not, we no need to find, but we all know a fact that sun doesn't shine every day, every time, right? So the energy or the power which we are getting is intermittent in nature. We doesn't have any problem to produce the power, but we need to find a way to store them. So when we think about the way to storing the energy, then the cost comes into play, and we need to design the electrochemical energy system in such a way that the cost will be effective for making them realize in practical. Okay, let me go a little bit about the battery introduction. So when we talk about the battery is nothing but it's a combination of two or more electrochemical cells connected in series or parallel based on our requirement. So Basically, in a battery, we have a anode, a cathode, and an electrolyte. So anode is a place where oxidation reaction occurs. Oxidation is nothing but the loss of electrons. And cathode is a place where reduction reaction occurs. It's a place where we actually the electrons will be accepted and get reduced. And electrolyte is a conductive medium which allow the transport of ions to flow through during the reaction process. So the general requirement of anode and cathode are that when we immerse this anode and cathode into the electrolyte, it should be in such a way that it should not be reactive. It should be stable in the electrolyte, and it should have good conductivity. But when we talk about the electrolyte, it should be ionically conductive. That means it should conduct the ions to pass through, but it should be electronically insulating. If you send the electrons, if the electrons pass through this, actually it will cause the short circuiting. Basically, when we create a battery or we develop a battery, we keep both the electrodes, anode and cathode, in such a way that they are in a minimum distance between each other, so that there is no internal short circuiting between them. Now, when we talk about the classification of batteries, commonly we are classified based on the physical and chemical energy. And in the chemical, we all know that there are primary batteries and secondary batteries. So when we talk about the primary batteries are nothing but the batteries where we have the active materials in the battery, and we will utilize all the active materials to drive our electrochemical reaction. After we utilize all the energy from the battery, we cannot use the battery later. That means we have to throw the battery off. That's the primary battery. That means it cannot be recharged or reused again. So the most commonly used primary batteries today are alkaline batteries, manganese oxide batteries, the carbon zinc batteries, where we use the zinc as an anode and carbon as a cathode. And then we talk about the secondary batteries. In secondary batteries are nothing but it's rechargeable batteries. It is a rechargeable battery where we can recharge it even after every use. If we fully discharge the battery, then we can recharge the battery by sending the current in the reverse direction. If you extract the current, then if you send the current in the reverse direction, then we can recharge the secondary batteries. So secondary batteries are also known as storage batteries or accumulators. So a good characteristic of a secondary battery is that it should have it has a high discharge rate. That means we can use it for a long time. It has a high power rate. We can deliver high power. We can have a flat discharge curve from a secondary battery, as well as it will show good temperature performance. And when we talk about the secondary batteries, we know that lead acid batteries, nickel metal hydride batteries, nickel cadmium batteries, lithium and sodium and batteries, sodium sulfur, lithium sulfur, everything comes under secondary batteries. So this is a comparison between the secondary batteries. And you can see that the lithium ion batteries are high or in the top front in the list. Actually, lithium-ion batteries are commercialized in the 1992. Sony commercialized it. So if you see that we can get a nominal voltage of around 3.6 to 3.7 from a single lithium-ion cell, you can see that the energy density and power densities are very high for the lithium-ion battery, as well as it can go for a very long cycle life, as well as the self-discharge rate. That means if you keep the battery, the discharge, if you do like if you take our cell phone, our discharge rate is low, but if you take the lead acid battery, the discharge rate will be very high. That's the thing, that self-discharge. If you keep something, if it's discharging at a very fast rate, then the self-discharge is very high for that battery. Now let's talk about the lithium-ion batteries initially. So lithium-ion battery, as I told, it was first discovered by Goodenough, where he used a graphite anode, lithium cobalt oxide cathode, as well as lithium hexafluorophosphate in methylene carbonate, propylene carbonate as the electrolyte. So when we these are the electrodes, and this is electrode. These electrodes are basically tunnel shape or layered shape, the structure of these electrodes. So how we get the capacity by driving the electrochemical reaction between these electrodes. And this is a Ragun plot, very famous plot basically in electrochemical energy storage system. It's a very important plot. It's a plot describes between the specific energy as well as specific power. You can see where the place of batteries, particularly batteries, lies in between supercapacitors and fuel cells. And batteries basically has a very high energy density when compared to supercapacitors. That means basically supercapacitor can deliver a very high power at a very short range, but batteries can store very high energy at a very short rate. And now when we talk about the lithium-ion batteries, you can see that this is again the Ragun plot, where you can see that the lithium-ion batteries are high, the performance is higher when compared to the other secondary ion batteries. Secondary batteries like lead acid, nickel cadmium, nickel metal hydride. You can see from this plot that lithium metal batteries are very it's having higher energy density. The reason because we are using the lithium metal as such, so we can get the maximum capacity out of it. But the problem with the lithium metal, if you use the lithium metal, then the major problem is the dendrite issue. There is something, a hair-like growth of issue, which is happening in this kind of batteries, which actually determines the performance of the battery. That's why people are going with the lithium-ion battery rather than lithium metal batteries. Okay, now let's go a little bit about the working of the lithium-ion battery. So basically, as I told, we have a positive electrode, we have a negative electrode. The positive electrode is nothing but the layered transition metal oxide, which contains lithium in it, basically. So here it's a lithium cobalt oxide or lithium manganese oxide or any layered transition metal oxide we can use here. And this is a graphite, it's a layered sheet. And you can see that during charging, the lithium transition metal oxide acts as anode and graphite acts as cathode. So the ions will move from anode to cathode during charging. So basically, as I previously told, anode is a place where oxidation reaction occurs. Thereby, it lost the electrons. So it gives the electrons to the external circuit. This negative electrode, what it will do, it will, the cathode, what it will do, it will receive the electrons and it gets reduced. So basically, lithium ions will move from here to here, and the electrons will move from here to here. This lithium ions will receive this electrons coming from here and get reduced here as lithium. So this is the mechanism during charging, and during discharging, it's vice versa. The lithium ions will move from this graphite to the lithium cobalt oxide. And the electrolyte here, it acts as a conductive medium for the transport of ions. And basically, the lithium-ion batteries, we have three kinds of anode mechanism. One is insertion type, one is alloying type, and another is conversion type. Insertion type is nothing but, you can see here that lithium ions are moving from here and sitting here. The graphite basically acts as a host for the for occupying this lithium ions. So basically, the lithium ions are intercalating and de-intercalating during charging and discharging. That's basically this intercalation mechanism or the insertion mechanism. And there is another type, alloying type, that's basically followed by silicon as well as tin-based materials, where this lithium will make a alloy with this compounds, and then the chemical reaction occurs. And conversion type is nothing but this kind of conversion type of mechanism is happening with transition metal oxide, metal phosphate, metal sulfate based materials, where this lithium will react with that and then get converted to another compound. That's the reaction there. And most commonly and widely people use insertion type of materials, because alloying and other conversion types has its own demerits, like there are heavy volume expansion during charging and discharging. Okay, so you all know the applications of lithium-ion batteries. Commonly, lithium-ion batteries are used in wide range of applications, ranging from electric vehicles, electric grid applications, to the portable electronic like smartphones, laptops, tablets, personal care, everything. Okay, so now I talk about the importance of lithium-ion batteries. Okay, then people will think that okay, if lithium-ion batteries are doing very good in the market, then why we cannot keep on using lithium-ion batteries, and why we have to find an alternative? Okay, if you see this plot, you can see that in the next century, the demand for lithium-ion will grow very high. If the demand is going very high, basically there will be a scarcity of lithium, and the minimum amount of lithium currently in the earth, we should pay very high amount of cost for getting there. So basically the demand will be high, the cost will be high. So this is the plot which shows that basically in the next century, the cost of lithium will surge a lot. Then researchers have thought that, okay, do we have any replacement for lithium? Yes, we have sodium. Sodium is basically, it has similar electrochemical properties like lithium. It has a standard reduction potential of 2.7 volt versus SHE. It is a lighter metal. It is the fourth most abundant element in the earth. So researchers are finding a way to replace the lithium with sodium. Now, when we talk about the alternative battery platforms, basically, if you see this energy density plot, you can see that lithium sulfur batteries are having more energy density when compared to the lithium ion batteries. So, but again, this is again lithium based material, right? If you use lithium, again, because of the scarcity, the cost will be very high. So we cannot make it realize practically. So then people thought of moving to sodium, and you can see that sodium sulfur batteries are having very high energy density when compared to sodium ion batteries, in fact. Now let's go to sodium sulfur batteries by making a comparison with the lithium ion batteries. How the sodium sulfur batteries mechanism compare from the lithium ion batteries or sodium ion batteries, because lithium and sodium ion, the ion differs, but the mechanism is similar. So as I told previously, we have two electrodes, we have electrolyte, we have the lithium ions moving here and there, the intercalation and deintercalation between the electrodes, and from that we are drawing the capacity out of it. But when we come to the sodium sulfur or lithium sulfur batteries, irrespective of the metal, the mechanism is similar. So let's take the sodium sulfur batteries. We have a sodium metal anode, we have a sulfur cathode. The sulfur cathode exits in S8 form. S8 is the most stable form of sulfur. S8 is in ground structure, and we have the sodium metal here. During discharge, what happens? The sodium ions will flow through the electrolyte, will pass through the electrolyte, and will come and react with the sulfur cathode. As I told previously, sulfur is in S8 form. Now the sodium will react with the sulfur to form sodium polysulfide. First intermediate product formed is Na2S8. This is the first reduction product with the reaction between sodium and sulfur. This Na2S8, instead of staying in the electrode, it will go to the electrolyte. Why? The reason is because we have an electrolyte. The solvents which we are commonly using in this electrolyte is DOA and DME. DOA is 1,2-dioxylene and DME is diethoxymethane. So when we use this kind of solvents, basically this sodium polysulfide intermediate which is formed, that is Na2S8, which is formed, will go to the electrolyte, because the energy, binding energy or the attraction energy of this electrolyte solvent with this polysulfide is stronger or higher when compared to with that of electrode. So when the adsorption energy is higher, basically it will go to the electrolyte. That's the reason why it's not staying in the electrode rather than going to the electrolyte. Now the picture is like, okay, sodium reacted with sulfur, we got Na2S8. This Na2S8 went to the electrolyte. Now again, it will reduce from Na2S8 to Na2S6. And from Na2S6, it will further reduce to Na2S4, Na2S2, so on and so forth to Na2S. So basically, Na2S8 will convert to Na2S. This is the conversion reaction. So Na2S8 is soluble in electrolyte. That's why it's going to the electrolyte, because of the higher adsorption energy between the electrolyte solvent and the polysulfide. Then it gets converted to Na2S. Na2S is the final discharge product. Now, now during the charging process, this is the final discharge product, and basically this Na2S is insoluble in nature. If it is insoluble, basically it cannot stay in the electrolyte, because electrolyte is in the liquid phase, this is in the solid phase. So either this Na2S will precipitate down, or it will again come and stick to the electrode. You can see that this Na2S is sticking to the electrode. Either it will stick to the electrode, or otherwise it will precipitate down. Now during the charging process, basically we just need the shuttling of sodium, right? But here Na2S is there. So this Na2S bond breaking should happen and it should leave the sodium back to its place. So this is the mechanism during the charging and discharging. Now, during the discharging phase, discharging is this direction. During the discharging phase, as I told previously, there is the polysulfide formation and going to the electrolyte. That is commonly called as shuttling of polysulfides. This is the very common major fact affecting the realization of sodium sulfur batteries. Now, second is poor kinetics of polysulfide conversion. That is nothing but, as I told, Na2S8 will convert to Na2S6, Na2S4, Na2S2, and Na2S. This conversion from Na2S8 to Na2S, this conversion is very kinetically very slow. So these are the major. So if it is kinetically very slow, basically we are taking long time to drive the electrochemical reaction. So we are taking long time to discharge, long time to run the process. So when we talk about the charging process, as I told previously, this Na2S should go, this sodium should go back to sodium metal anode during the charging process. So because of the poor conductivity of this Na2S, the charging process is also difficult. Okay. Now, when we talk about the experimental voltage, this is basically a voltage profile, and this is the profile. You can see that this is plotted between the voltage as well as the specific capacity. You can see that, as I previously told, the sulfur is in the S8 form, and during the discharge, S8 will convert to Na2S8. As I told previously that Na2S8 is in the liquid phase, it will go to the electrolyte rather than staying in the electrode. That's called shuttle effect. And this is basically a solid to liquid transition. And this is the reaction. S8 will react with the sodium with the electrons to form Na2S8. This will have a capacity of 200. And when we drive the reaction from Na2S8 to Na2S6, S4, S2 to Na2S, we will get the maximum capacity out of it. So the idea which you have to take from this plot is basically that if you have to get the maximum capacity from the sodium sulfur battery, you have to drive the reaction to the complete end. That means you have to drive the reaction for the formation of Na2S. Only after the formation of Na2S, you will get the complete capacity out of this battery. Suppose if you stop the, because as I told that this Na2S is insoluble in nature, right? It will go and stick on the electrode. Suppose if a researcher thinks that we have to stop the reaction at Na2S4, then basically we are getting only half the capacity out we can derive from that particular battery. And these are the reaction steps for this process. Okay, now I have talked about the major issues and problems in the sodium sulfur batteries. Now what our lab is doing, so basically I told that this there is a shuttling effect problem, there is a poor kinetics problem, and when we are talking about the charging, then there is a problem with the poor conductivity of sodium Na2S, so that it's difficult to charge the battery. So in our lab, what we are doing, we are developing a kind of catalytic active anchoring material which can bind this polysulfide so that it won't allow the polysulfide to go to the electrolyte. It will convert the polysulfide from Na2S8 to Na2S at a very faster rate. And during the charging process, it will break the sodium sulfur bond and allow the sodium to diffuse very fast when compared to the pristine sulfur cathode. Now, so basically first we started with the single atom catalyst. So what is single atom catalyst? So single atom, as the name indicates, is just a single atom. So either a transition metal atom, just a single atom. Why we are using a single atom? The reason, because if you have a single atom, we have a maximum utilization efficiency from this catalyst. If you have a bulk catalyst, something like a cluster, then basically the utilization of each atom towards the performance is very limited. That means every atom won't be involved in the catalysis. But if we have a single atom, that single atom will have the entire site to react, and the catalytic efficiency will be more when compared to the bulk catalyst. So that's why we used a singleton catalyst. And in our study, we used chromium, iron, and cobalt-based singleton catalyst for binding the polysulfide as well as converting the polysulfide. We also, this is another work where we use BS2. BS2 is vanadium disulfide. Vanadium disulfide is, you all know that it's a conductor, so it's conductive in nature. We actually use these two materials as an anchoring material to see whether it can bind the polysulfides rather than sending it to the electrolyte, whether it can convert the polysulfides, and during the charging process, whether it can break the polysulfide bond, and whether it can diffuse the sodium ions to the anode itself. Now, if you go to any sodium sulfur or lithium sulfur battery literatures, you can find one fact that any carbon-based material cannot bind the poly. If you use a carbon-based material here, and if you mix this carbon with the sulfur, and if you use this as an anchoring material, there is no report which can show that this carbon material can bind the polysulfide. Basically, if we use any carbon-based material, it won't bind this polysulfide. Again, because of the interaction energy between the polysulfide and electrolyte, it will go to the electrolyte rather than staying in the electrolyte. Now, if you see, we actually proved that from our DFT calculations. This is actually the interaction energy between the electrolyte as well as the sodium polysulfide. And this is the interaction energy between our carbon or the graphene with the polysulfide. You can see that the interaction energy between the carbon and the polysulfide is very low when compared to the interaction energy between the electrolyte and the polysulfide. So basically what happens, since the interaction energy is higher with the electrolyte and the polysulfide, it will go to the electrolyte rather staying in the electrode. Now, when we use the singleton based catalyst, you can see that the interaction energy is significantly improved. And you can see that the interaction energy is very high when compared to the interaction energy with that of electrolyte. So that what happens, it will bind the polysulfides within the electrode rather than sending it to the electrolyte. Now, as I told here, okay, then you can ask like, okay, what's the reason why graphene is not binding the polysulfide? The reason is because you can see here clearly that there is no bond formation in all these polysulfides. There is no bond formation. That means that there is just a weak physical van der Waals interaction between this polysulfide and the graphene, which is making them bringing in tight. There is no chemical bond formation. Because of no chemical bond formation, there is no stronger chemical interaction between these two systems. Now, when we talk about the singleton catalyst, you can see clearly that there is a bond formation and there is a strong, this is sulfur, this is sodium. There is a strong sulfur transition metal bond, as well as there is a sodium nitrogen bond. So basically, because of that, the chemical interaction is increasing, and as a result of that, our binding energy increased. And basically we found that if we use this kind of singleton catalyst, we can trap the polysulfide rather than sending it to the electrolyte. Now we also use VS2 based material. VS2, as I told previously, it's a conductive in nature. So this is basically the interaction energy between the electrolyte and the polysulfide. You can see clearly that compared with the electrolyte interaction energy with the polysulfide, the interaction energy between the VS2 and the polysulfide is very high. That means that VS2 material also can trap the polysulfide rather than sending to the electrolyte. This is the binding configuration of this. This is Si2 to VS2, Na2Si to VS2, Na2Si to VS2. This is the binding configuration. We convert the structure and later we calculated the adsorption energies. And I was always talking about the interaction energy between the electrolyte and the polysulfide, right? What it is. This is the electrolytes. This is the electrolyte solvent. This is DOL, dioxylene, and dimethoxyethane. These are the electrolyte solvents commonly used in sodium sulfur batteries, and this is the interaction energies between these two. If the interaction energy of this system is higher than this system, then it can trap the polysulfides without sending to the electrolyte. Now we have found that the adsorption energy of single atom catalyst as well as BS2 is very high compared to that of the electrolyte. So we have to find the reason why it's high. Then we do the analysis. First analysis what we did was ratio of van der Waal analysis. So if the van der Waal interaction is higher basically, then the chemical interaction will be lower, then there won't be much interaction between them. So first we talked about the carbon-based material. You can see that for the carbon-based material, the ratio of van der Waal interaction is very high. That indicates that there is only a van der Waal interaction between the carbon and the carbon and the polysulfide, and because of that the interaction energy is weaker. But when we go to the single atom catalyst, you can see that the ratio of van der Waal interaction decreased and ratio of van der Waal interaction decreased. If the ratio of van der Waal interaction decreased, that's a sign that the chemical interaction in that system is increasing, and the chemical interaction is very high for the Na2s. Why? Because the ratio of van der Waal interaction is very low for the Na2s. If it is very low for the Na2s, that means that the chemical interaction is very high for Na2s. That's the reason why you can see here that Na2s binding is very higher when compared to Na2S4 and Na2S8. Na2S binding energy is around 3 eV. That's the reason why the chemical interaction is higher. That's the reason for the higher binding energy. And this is for the VS2 substrate. And for the VS2 substrate also, for the S8, you can see that this is the VS2 substrate. For the S8, you can see that there is no chemical interaction between them, only the weak physical interaction. That's the reason why you are seeing maximum ratio of van der Waal interaction from that. But when we move down the line from S8 to Na2S, you can see that Na2S has the lowest van der Waal interaction. That means it has the highest chemical interaction. That's the reason why Na2S has higher binding energy when compared to the other systems. Now we have calculated the charge transfer, basically how much charge is getting transferred between the system. So this is the graphene and this is the single atom catalyst. You can see that the single atom catalyst has the higher charge transfer when compared to the other systems, and in particular you can see that Na2S has higher charge transfer when compared to other polysulfide adsorbed systems. That's the reason again why Na2S has higher binding energy when compared to other systems. Now this is nothing but the charge density difference profile, where we can find where the charge is accumulated, where the charge is depleted, actually where the charge is. To find that, we actually did this analysis, and the red color indicates the charge accumulation and the green color indicates charge depletion. From this you can see that the charge is basically accumulated at the interface between the substrate and the polysulfide, and the charge is depleted from the polysulfide itself. Even for VS2, you can see that the charge is accumulated at the interface and the charge is depleted from the polysulfide. That basically indicates that the charge is getting transferred from the polysulfide to the substrate. That's the reason why we are getting a positive charge transfer value in our calculations. If we get a positive charge transfer, that indicates that the charge is getting transferred from the polysulfide to the substrate. Now we have done the density of state analysis to check, okay, how the conductivity before adsorption and after the polysulfide adsorption, how the conductivity changed. Now we all know that graphene is a zero band gap semiconductor, right? You can see here clearly it's a zero band gap semiconductor, but when we put the polysulfide, you can see slight states at the formula. Now, when we talk about the single atom catalyst, even before the polysulfide, just the pristine single atom catalyst, if you run a band calculation, we found that the single atom catalyst itself is conductive in nature. That means it can conduct the electrons between the states. Between the bands. Now, even after the polysulfide adsorption, even after Na2S8 adsorption, Na2S4 adsorption, Na2S adsorption, you can see that there are states at the Fermi level. That clearly indicates that even after the polysulfide adsorption, the conductivity is retained. There's no problem with the conductivity. So basically, if the conductivity is retained, that actually boosts the electrochemical performance. How? There is always a path for the electron pathway, right? So it can easily conduct the electrons. So that because of that, there is no problem with the electron conductivity, and we can boost the electrochemical performance of the sodium sulfur batteries. And again, we have a BS2 material. You can see that BS2, as I previously told, it's conductive in nature. You can see clearly that the total is nothing but the density of states of the pristine BS2. You can see that the BS2 itself is conductive in nature, and even after polysulfide adsorption, you can see that at the Fermi level, the conductivity is retained. And you can see from this density of state that, okay, you can ask that which state is majorly responsible for this conductivity. We could tell that the vanadium 3D state, you can say that the vanadium 3D state, this is red color. If you see at the Fermi level, this is a Fermi level, you can see at the Fermi level that the vanadium 3D state are more when compared to other states. And you can say that, you can see from here that there is some overlapping between the vanadium 3D state as well as the sodium polysulfide. That's basically the bond formation. When we have a bond formation, we have a hybridization or the overlapping of orbitals. That also you can see from this DOS terms. And now we have talked about the shuttling. And there is another effect when we talk about the discharge. As I previously mentioned, one is shuttling and the other is the poor conversion from Na2Si to Na2S. That also we actually studied with our BS2 material. And as I previously told, during discharge, S8 will convert to Na2S8, Na2S8 to Na2S6, Na2S4, Na2S2 to Na2S. This is the final discharge product. When we talk about this conversion in the vacuum or without any catalyst, you can see that among all the steps, this step has the highest value. That means it is the rate determining step. Basically, the step with the highest value is the rate determining step or the most endothermic step in the overall reaction. In our sulfur reduction reaction process, you can see that Na2S4 to Na2S2 conversion is slower with a higher value. But when we put that on the BS2 substrate, we found that this value significantly reduced from 1.442 to 0.546. That clearly means that if you have a BS2 material, then it can easily convert the polysulfides without any hassle. The conversion rate of polysulfides with this substrate is very high. And even this Na2S2 to Na2S conversion is around 0.720. It's also endothermic in nature, but when we put that on our VS2 substrate, then it can easily convert the polysulfide and the reaction is exothermic in nature. Now, I have talked everything about the discharge. We have the shuttle effect, we found the binding energy calculations, and then we went to the sulfur reduction, how the polysulfides are getting converted. Now we have Na2S. Now this Na2S is the final discharge product. It should go back to its normal state during charging. Basically, how this Na2S will be there, it should break and Na should go back. Na should diffuse and go back. So for this, we should have a sodium and sulfur bond breaking. Only after breaking this bond, the sodium ions can go. But for that, during the charging process, we actually calculated the catalytic decomposition or the NEB, based on nudge elastic band calculation. We calculated the bond breaking of sodium sulfur, and we actually calculated how the sodium ion will be diffusing. So when we calculated the bond breaking, we found that for the pristine Na2S, if you have a simple Na2S without any catalyst, that bond breaking will happen at 2.44 electron volt. It's very high actually. But when we put that on a single atom catalyst, you can see that the bond can be easily broken and sodium can be easily gone. How you can see that? From a very low energy barrier. It's like the energy barrier is only 1.54. You just have to cross this energy barrier to make this reaction to happen. But when again, this is for the single atom catalyst. Again, when we use the BS2 based catalyst, you can see that this value from 1.17, this is the lowest value here. This value even reduced from 1.17 to 0.53. That means basically if we use a BS2 catalyst, it can do very good in the discharge process. It can easily convert the Si to Na to S, and during the charging, it can easily break the Na to S and send the sodium ion because it has a very low catalytic decomposition barrier. Okay. Now this is another one work where we worked on MOS2 based material. Basically, we all know that MOS2 is a semiconductor, direct band gap semiconductor with a band gap of 1.6 electron volt, right? Okay. In previous literatures, you can find that MOS2 edge sites are active for polysulfide adsorption. So if we have to increase the catalytic efficiency of a substrate or a material, basically we have to increase the active sites, right? We have to increase the active sites to increase the efficiency. So we all know that the edge site is active, but for us, we have to, if we can make the basal plane to be active for the polysulfide adsorption, then both the basal plane as well as the edge site will be active, then the more efficiency the catalyst will be. So in order to activate the basal plane in the molybdenum disulfide, we actually dope the single atom catalyst at 3 favorable sites. One is sulfur substitution site. This is sulfur. We substituted on sulfur. And another is molybdenum substitution site. We basically substituted on molybdenum with the transition metal. And another is molybdenum top site. This is molybdenum top site. And then we calculated the binding energy of this. We actually choose 3 transition metals for this study. One is vanadium, iron, and nickel. So this is sulfur substitution, molybdenum substitution, MO top site, all 3 sites. We calculated the binding energy of the polysulfides with this substrate, and we found that the binding energy of the substrate with the polysulfide is higher than this is the binding energy of the polysulfide with the electrolyte, and the binding energy of this substrates with the polysulfide is very higher when compared to electrolyte. Even for the MO top site, we found that it's very higher. But even if we go to the MO substitution site, these values are the binding energy of the polysulfide with the electrolyte is higher when compared to that of the substrate. So basically we found from this analysis that sulfur substitution site and molybdenum top site are good for trapping the polysulfide, but not the molybdenum substitution site. This is basically the geometric configuration of the adsorption of the polysulfides with the substrate. Now this is a first time we are actually doing this analysis for a battery, and this is basically a D-band center analysis. You might be knowing that D-band center is a very good descriptor for understanding the catalytic performance of a substrate. So basically this is the Fermi level. This is valence band, this is conduction band, this is the Fermi level. If the D-band center of the transition metal, if it is very close to the Fermi level, then the binding energy will be higher. If the D-band center is very farther from the Fermi level, the binding energy will be lower. Why? Because there are 2 kinds of molecular orbitals. One is bonding molecular orbital, other is anti-bonding molecular orbital. So bonding molecular orbital, so if this is the basically this is the Fermi level, the bonding molecular orbitals will be around here, and bonding molecular orbitals will be completely filled. The anti-bonding molecular orbitals are the ones which are near to the Fermi level. So that's why we are using D-band center as a descriptor for understanding the catalytic performance. Why? Because the D-band center of the transition metal is closer to the anti-bonding molecular orbital. If we know where the D-band center is, we can know where the anti-bonding molecular orbital where it is, because bonding molecular orbital is already filled. We cannot fill that. We need to fill the anti-bonding molecular orbital. If the anti-bonding molecular orbital is very close to the Fermi level, it can easily be filled. Now, by keeping all these things into consideration, if you see this one, we actually studied here vanadium, iron, and nickel. If you see here, vanadium, this is the Fermi level, this line, and this is the D-band center. The D-band center for the vanadium is close to the Fermi level when compared to iron and nickel. Here the nickel is very far from the Fermi level, and the dependent center is far. But for the vanadium, the dependent center is close to the Fermi level. That's the reason why for the vanadium, it can easily fill the electrons. Because of easily filling the electrons, you can see that the vanadium has the highest binding energy when compared to iron and nickel. If you see all this, the vanadium has the highest binding energy when compared to iron and nickel. Why? Because its dependent center is very close to the Fermi level. If the dependent center is very close to the Fermi level, the adsorption energy is very high. Again, we actually studied the discharge. Okay, what now we proved here that okay, our material can bind the polysulfide, so we can suppress the shuttlity. Now we need to find whether our polysulfide conversion mechanism is faster or not. We already know from the previous value that 1.442 is the rate determining step in the overall reaction process, and for the pristine MOS2, the value reduced from 1.442 to 0.857, and when we put the singleton catalyst, you can see that the value significantly reduced. That means that the singleton catalyst can easily convert the polysulfides. Easily it can convert the polysulfides from one to another. Now, when we talk about the charging process, as I told that, okay, we have the Na to S, we have to send the Na back, right? For that, we actually calculate the charging mechanism, and we found that compared to sulfur substitution site, MO top site has very low value, because if you see, compare this to 0.83 is the lowest value. And that happened for the vanadium. Why? Because vanadium as a, so this is our substrate. This is the vanadium atom, single atom. This is the sulfur bond, vanadium sulfur bond. So this is our sodium. This is the Na2S, Na2S. So if the vanadium makes a very strong binding with the sulfur, then this bond can break related to this bond. That's the, I already told that vanadium has a very stronger binding energy because of its dependent center closer to the Fermi level. That's because vanadium has a very strong energy with the sulfur. That's why the sodium ion will break. That's why we found that it has very low catalytic barrier, so it can easily break the sodium sulfur bond. Okay. Other than that, other than the batteries, in our lab we also work on nitrogen reduction reaction. We actually basically reduce the nitrogen to ammonia. We actually work on the oxygen evolution reaction. We split the water into oxygen and hydrogen. Basically, I'll just go through that what we are doing other than the batteries in our lab. So basically, you all know that Haber's process is a very famous process for the conversion of nitrogen to ammonia, right? So Haber's process is a high temperature as well as high pressure process. So if we need a high temperature and pressure, we need basically high cost to do that. So there is another viable method to do this. It's an electrochemical method where we can electrochemically reduce the nitrogen to ammonia using a electrocatalyst. So in our work, we used endohedral fullerene as a catalyst for the conversion of ammonia to for the conversion of nitrogen to ammonia. So you can see here that endohedral fullerene is nothing but it's a 0-dimension carbon nanotube, and we actually put this is nothing but it's a metal atom encased inside the fullerene. So these metal atoms are nothing but the scandium, and this is nitrogen. For this study, we actually choose 5 materials. One is scandium nitride D5H, scandium nitride IH, scandium nitride D3HC78. This is varying the carbon atoms in the ring, and this is Y3N, yttrium nitride, as well as uranium. We actually studied these 5 these 5 compounds for nitrogen reduction reaction. So before going to that, I need to tell you what are the major things we have to look when we are doing a nitrogen reduction reaction. First thing is that the name indicates it's nitrogen reduction. So we have to adsorb the nitrogen to the substrate. So the catalyst which you are choosing, it should preferentially adsorb this nitrogen to the substrate. Then it has to convert this nitrogen to ammonia. For the conversion, there is a step. This nitrogen N2 will convert to NNH with the addition of proton. Then the NNH will convert to N2H2. with again the addition of proton. Then this NNH, again this will convert to nitrogen. This not nitrogen, it's N radical. Then again we will add a proton, then it will go to NH, then again NH2, NH3. This is the pathway for nitrogen reduction reaction. There is another one pathway, enzymatic pathway. This is distal pathway, alternating pathway, enzymatic pathway. The difference between these two pathways is nothing but here, if you see, the nitrogen is binding in the end-on configuration. Here, the nitrogen is binding in the side-on configuration. If it is binding in the side-on configuration like this, then it will follow the enzymatic pathway. Otherwise, it will follow the distal pathway. Now, if you have to convert the nitrogen to ammonia, first thing is we have to preferentially adsorb the nitrogen. Second thing is this pathway should have a very low potential determining step. If it has a very low potential determining step, it can easily convert from nitrogen to ammonia. The third thing is the competitive mechanism between the nitrogen reduction reaction and hydrogen evolution reaction. Why? Because you can see that here it is nitrogen, but we are adding a proton, right? Proton is nothing but H plus. So when we add a proton, this proton can adsorb on the substrate rather than, like, suppose if we have a proton, this proton, instead of going and sticking here, it can go and stick here, right, to the substrate itself. So then there is a competitive mechanism, whether the proton has the highest binding energy with the substrate or the nitrogen has the highest binding energy with the substrate. That also plays a role in the nitrogen reduction reaction. And this is the Gibbs free energy plot where we have the conversion from nitrogen to ammonia. And this is the, as I told, that the energy step with the highest value is the potential determining step. If you see the entire steps, you can see that this is the potential determining step in the overall reaction process because it has the highest energy upkeep value. And I previously told that there is a competitive mechanism between HER and OER. So we actually calculated our 5 materials for HER and OER, and we found that this is NRR activity and this is NRR selectivity. So basically the 3 materials are at the rightmost corner. That means that it has very high NRR activity as well as it has very high NRR selectivity. And as I previously mentioned, we actually studied 5 materials. This is the first material and these are the other material potential determining steps. And you can see that for all the materials, N2 to NNH is the potential determining step in the overall reduction process. And as I previously mentioned, we studied 5 materials and you can see that among the 5 materials, only U76 is HER dominate when compared to NRR dominate. Why? Because you can see this one. This is the HER evolution reaction Gibbs energy plot. And basically, you all know that the platinum is a very best catalyst for splitting the water and for the hydrogen evolution reaction. So basically, this is the thermoneutral value. Thermoneutral value is nothing but the value at the 0, and platinum is something around here. The platinum has the value around here. So we found that for a uranium C76, it's very close to the thermoneutral value. That's the reason why the uranium C76 has more activity towards HER when compared to NRR. For the other systems, the HER values are higher. But for uranium C76, the HER is very close to the thermoneutral value and it's very close to the platinum value. That's why it is showing very good performance for HER when compared to other systems. Now, in our lab, we also work on the oxygen evolution reaction. We split the water into hydrogen, oxygen, and basically oxygen evolution reaction occurs at 1.23. If you split water into hydrogen and oxygen, it basically the reaction occurs at 1.23. Hydrogen evolves at 0 volt, but oxygen evolves at 1.23 volt. But in actual condition, if you want to split a water, you cannot see that water will be split at 1.23 volt. It will split more than this way. Because why? Because there is some kind of overpotential or some kind of barrier we have to cross to split the water. So in order to reduce that value, we are actually working on catalysts for reducing the overpotential to split the water at a very faster rate. So for this study, we used a cobalt sulfide nickel vanadium layered double hydroxide heterostructure if this is a heterostructure, we made a heterostructure, and this is the charge density difference plot. Again, I told that this is to find that where the charge is accumulated, where the charge is depleted. Basically, you can see that the charge is getting transferred from the nickel vanadium LDH to the cobalt sulfate, and how much charge is getting transferred? 1.1, around 1 electron is getting transferred. And for nitrogen reduction reaction, I told that there is steps like N2 to NH3. There are some conversion steps. Same like nitrogen reduction. For oxygen evolution reaction also, it's 4 electron process where OH will be. I actually considered our reaction in the alkaline medium. There is another one, acid medium. In acid medium, we consider a pH is equal to 0. In alkaline medium, we basically consider a pH is equal to 40. So this is a 4 electron process. 4 electron process is basically from OH to this, from OH to O, from O to OOH, from OOH to basically H2. This is the conversion reaction for the oxygen evolution reaction. So as I told previously that we made a heterostructure with the nickel vanadium LDH and cobalt sulfate. We actually calculated the DOS for the cobalt sulfate. We found that it's actually in the Fermi level we have states, so it's conductive in nature. Then we found that even for the nickel vanadium LDH, we have states at the Fermi level, so it's also conductive in nature. When we made the heterostructure, we can also find the states at the Fermi level. So basically, even after the heterostructure formation, our conductivity is retained. And as I previously told that OER is a 4 electron step. So we have to convert the OH to H2O. This is the conversion steps. OH will convert to O will convert to OH, OH will convert to O2. And this is for the pristine nickel vanadium LDH. For pristine nickel vanadium LDH, this conversion, the highest energy step is OH to O step, and with a higher barrier of 1.85 volt. But when we made a heterostructure, we basically found that this value reduced to 1.68. That means this, after the formation of heterostructure, because of the synergetic interaction between the substrates, it can easily convert OH to oxygen, OH to oxygen. By that means we can split the water at a very faster rate with a very low power potential. And as I told previously, when we split water, we have hydrogen as well as oxygen. So now we found about the oxygen. Oxygen is evolved from OH to H2, and basically we have another one. It's hydrogen evolution, right? So as I previously, you see this kind of plot in the nitrogen reduction reaction. Similar kind of plot you can see here. For the pristine nickel vanadium LDH, the value is very far from the thermoneutral value. It's very far, but for the after making the heterostructure, this value reduced, and it's closer to the thermoneutral value. That indicates that it has a very good HR characteristic. How we actually examine this, why it's showing very good HR property? We actually, again, now we come to the concept of D band center. As I previously told, this is the Fermi level. If the D band center is very close to the Fermi level, it has good adsorption characteristics. Now, for the hydrogen adsorption, if you consider a catalyst, if you put the hydrogen, we have hydrogen here. If the hydrogen gets adsorbed very strongly to the substrate, then we cannot take the hydrogen back. If you see the reaction steps here, hydrogen comes and sits on the substrate, then we have to convert that into H2. So basically hydrogen should adsorb, then it should dissolve from the substrate. If the hydrogen sticks if the hydrogen binding energy with the substrate is very strong, then basically we cannot take the hydrogen back. So for the HER, you should keep in mind that it should have a moderate adsorption. In contrast with the battery, in battery we found that if it is very close to the Fermi level, it should have a very high, it will have a very high adsorption energy, then it can prevent the shuttle effect. But here, hydrogen should be adsorbed at a moderate range so that it can adsorb and later dissolve from the surface. So you can see that for the pristine nickel vanadium LDH, the value is around 1.093 from the Fermi level. But after making a heterostructure, the value reduced to 1.240. Basically, it's moving farther from the Fermi level. So as I told previously, the more farther from the Fermi level, the more weaker the binding energy is. but we need a weaker and a moderate binding for Here. That's the reason why after making the heterostructure, our material showed a very good property for Here, because it has a d band center very far from the Fermi level. The d band center very far from the Fermi level, the weaker the binding energy is. That's why we can adsorb the hydrogen and dissolve the hydrogen faster. So that's the works we are currently doing. And the summary, actually, I talked a little bit about the electrochemistry, then about the batteries, the classification of batteries, then the importance of lithium-ion battery, and why we are transitioning from lithium-ion battery to sodium-sulfur batteries, and little bit about the anchoring materials, how we can trap the polysulfide, how we can convert the polysulfide, how we can how we can send the sodium-ion back during the charging process. And I also talked a little bit about what we are doing on the nitrogen reduction reaction, oxygen evolution reaction. If you have any doubt, you can go anytime. You can contact me. And I would like to thank my advisor, Dr. Mahbub Islam, as well as my lab mate, Herein again, for his contributions. Thank you.
Thank you, Rahul, for your nice presentation. I think we can open the floor for the Q&A session. So if you have question, you can ask. You can unmute yourself and ask the question, or you can also use the chat box to ask. Hello, Rahul. Can you hear me?
Yeah, I can hear you.
Okay. I think we don't have any question from the audience.
Okay. Okay.
So thank you everyone for attending the webinar. Also, thank you so much, Rahul.
Yeah.
Thank you all. Thanks all.
Thank you.
Have a good day.